In quantum mechanics, Schrödinger equation is equivalent to Newton's law in classical physics. There are two types of Schrödinger equations. One is a time-dependent Schrödinger equation. The other is a time-independent Schrödinger equation. In this chapter, we're going to introduce time-independent Schrödinger equation. In this equation, psi is called a wave function. A postulate in quantum mechanics says that the state of quantum mechanical system is completely specified by a wave function. All you need to do is solve this Schrödinger equation. You get the wave function, and then you know everything about the system. Let's look at the Schrödinger equation in more detail. In this equation, h bar is a constant, which is Planck constant divided by 2 pi. So it's still a constant, and we sometimes also call this Planck constant. M is the mass of the system. If we study electrons, this is the mass of an electron. If we study a molecule, then this is the mass of that molecule. Okay. V is the potential energy of the system, and E is the total energy of the system. This equation is equivalent to this familiar second-order differential equation. We just replace y by psi. All right, and the second derivative of y here is the second-order derivative of psi over x. Now, in mathematics, okay, any operation can be considered as an operator operates on a function. For example, we can think about 5 times as an operator. So an operator is 5 times. Then if we write this operator operates on x, that means 5x. If this operator operates on 10, then that means 5 times 10, that's 50. Okay. Similarly, we can think about sine as an operator, derivative as an operator, and the second derivative can also be an operator. For example, if operator is second derivative, then this operator operates on 10 will give you 0, because second order derivative of 10 is 0. Or this operator operates on x squared, should be the first derivative is 2x and the second derivative is 2. So this gives you 2. So we can use operator to simplify the mathematical operation. So now let's look at the Schrödinger equation. We can recognize that the first one is the second derivative. So we can use an operator to represent this second derivative. Now you may remember in the last 2 sections we went over classical physics, and the kinetic energy is written as half mv squared, and we can also write half mv squared or 2m p squared. So the momentum squared divided by 2m. If you compare these two, you can see they resemble each other. So it also has a 2m. Okay, here 2m. The other things, maybe the momentum related to momentum in quantum mechanics. In fact, this second derivative, okay, a whole thing is called kinetic energy operator. Okay, just like in classical physics, it's the kinetic energy. Here, it's an operator, but called the kinetic energy operator. And this potential energy times psi is considered as a potential energy operator. Okay, so the left side has 2 operators. One is the potential energy operator. One is the second order derivative and considered as a kinetic energy operator. So if we combine these 2 operators together, we can use one symbol. It's called the Hamiltonian operator, which represents the total energy operator. And therefore, by using one operator to represent the 2 operators, the Schrödinger equation becomes very simple. The Hamiltonian operator operates on the wave function, give you function back times total energy. Okay, note that even though we just write as h bar or h as an operator, it actually a second order derivative. Okay, derivative on this side plus a potential energy times psi. So the equation is actually a second order differential equation. Suppose you solve the Schrödinger equation and you have the wave function psi. What information can you get? Now here is one of the most important postulates in quantum mechanics. It says that the wave function psi mathematically describes the wave characteristic of a particle. The value squared is related to likelihood of the particles being there at the time. In other words, wave function psi has no meaning, but when you square it, it tells you the probability density of finding the particle at a certain point. Okay, so if it's one dimension, all right, the square of the wave function gives you the probability at point x. Then if you times dx, that tells you the probability in the infinitesimal small amount range dx. Okay, now if you want to measure the probability in a measurable range from A to B, then you need to integrate. Okay, squared of the wave function, integration of x from A to B. All right, now if it's a 3-dimension, all right, then you still square it. That gives you the point probability density, and then you times a small volume, that's this one, dTau, integration in the space from tau1 to tau2. Okay, now remember, wave function itself has no meaning, and therefore when you solve Schrödinger equation, sometimes you get an imaginary number. All right, wave function can be imaginary, that's okay. So if it's a complex number which includes imaginary number, then how do you do that? All right, that's why in this equation you have a two vertical lines. So here we use wave function squared, but you have two vertical lines, and that means if the wave function is a real number, then this is just the wave function squared. But if it's a complex number, okay, then you need to, this symbol means it's conjugate of the complex number times wave function, it's wave function. Okay, for example, a complex number is a plus bi, and the conjugate will be a minus bi. So when you multiply these two, it will give you a squared minus b squared. That's a real number. So even if you get a conjugate, a complex number of wave function, that's fine. Wave function does not have a physical meaning, but when you square it, it always gives you a real number, and that tells you the probability of a certain point. Example, if we have a wave function y equals square root 3 times 1 minus x, okay, usually we use psi. Okay, the question is, what is the probability between 0.5 to 1? So 0.15 is here. We want to find the probability in this range. So this is the plot of the wave function in this case. In order to find the probability, you must square it. All right, so here is the squared of the wave function, and this is the plot. And from the plot, you can see the wave function probability is the highest in the left side, which is close to the origin. So in this range, you have the highest probability. Particles is more likely near the origin. And when you increase the distance, then you see the probability decrease and eventually becomes 0 at 1, okay, when x equals 1. Now to calculate quantitatively the probability between 0 to 1, then you need to integrate. You square it, you integrate from a to b. A is 0.5 and b is 1. Okay, so you need to write this equation to represent the probability from 0.5 to 1. And then you do some mathematics integration, and the answer is 0.04. We just learned that to calculate the probability of a particle from a range A to B, you square the wave function, then you integrate from A to B. Okay, if a wave function is a complex number, then you use the conjugate times wave function and then integrate from A to B. Okay, so that's the probability in range A to B. But what is the probability in the whole space? Okay, if the particle does exist, then the probability in the whole range must be 1. Okay, and therefore you have this equation. So this means from negative infinity, positive infinity means in the whole range, the probability, so you can write as psi squared. That's for real number, and for complex number, you use conjugate times psi, and that equals 1. So either using this form, or you use psi squared dx equals 1. All right, that's called the normalization condition. So for 3D, you use a small volume integration in the whole space equals 1. Example: in wave function psi equals n times a minus x, n is an undetermined constant. Find n. So here we have a range from 0 to a. X is a point inside the range, and the wave function inside this range is described by this equation, in which n is a constant that we want to find out. Okay, so it's an unknown. Okay, we want to find out. To find out n, okay, we use the normalization condition. Means that the probability to find the particle in this range is equals 1. So the wave function squared integration must be 1. And in this case, the wave function is n times a minus x. Plug in this equation, all right? You get this equation. Note that n is a constant, even though it's unknown, but it's a constant. So when you integrate, you move out of the integration. And if you spend a little time to integrate this one, and you will get that this integration is a to the 5th power divided by 3. Okay, so plug in this value and you can calculate n. So we have determined n, which is square root 3 over a to the 5th power. Then go back to this equation, all right, replace n, and so now we have the normalized wave function, which is square root 3 over a to the 5th power times a to the minus x. So the normalized wave function means now the particle described by this function has a probability of 1 in the whole range. Not all functions can be wave function. There are constraints on the wave function. So for example, wave function cannot assume an infinite number. All right. The reason is, if this is the wave function, and when you square it, it tells you the probability at x is infinite, and then that cannot be true. So wave function can't assume an infinite number. Second, wave function must be single valued. Okay, because each location should have only one probability. So if this is the wave function, and at x you have 3 values of wave function, and when you square it, it tells you at x you have 3 probabilities, and that cannot be true. Okay, so must be single valued. Wave function must be continuous. All right, so this function is not continuous at this point x, and that means at x, if this is the wave function, you have 2 probabilities. Again, it's wrong. Okay, can't be true. And lastly, wave function, the first derivative must be continuous. So in this function, the slope, okay, suddenly change at this point, and so the slope is the derivative. So this function does not have continuous the first derivative, so this can't be a wave function. This is because Schrödinger equation is about the second derivative. Okay, it's second differential equation. If the wave function does not first derivative is not continuous, then it doesn't have second derivative, so it can't be a wave function. So far we have talked about the wave function, and now let's talk about the operator. We already know some operators. In Schrödinger equation, we have potential energy multiply a wave function. So this potential energy multiply is an operator called the potential energy operator. And we also have a kinetic energy operator, which is negative 2m h bar squared second derivative of the wave function. And so this second derivative is called the kinetic energy operator. Now there are many more operators in quantum mechanics, and this postulate says that for every observable of the system in classical mechanics, observable is something you can measure, a position, momentum, or energy. These are all observables. In quantum mechanics, there exists a corresponding operator. So for kinetic energy, which is observable, in quantum mechanics, we have this operator. All right. In classic mechanics, we have potential energy, and in quantum mechanics, we have potential energy operator, which is just potential energy multiplied by a function. Okay. So what this means that in laboratory, we measure these observables. Okay, we measure position, momentum, but in quantum mechanics, we are not going to measure them. We are going to calculate them. In order to calculate these observables, we need to have a mathematical equation, and observable operators is used to formulate an equation, and then we can calculate these observables. Here shows some frequently used operators. We already seen kinetic energy operator, potential energy operator, and when you add these two together, that gives you total energy operator, which is also called Hamiltonian operator. And the Schrödinger equation, just the Hamiltonian operator, operates on wave function, give you function back times E. So the equation is also called eigenvalue problem. Now, position energy operator, okay, this one is just the position multiply. And the momentum operator has two forms. Okay, let's choose the second one. So momentum operator you can write as h bar divided by I, first derivative. Okay, note that kinetic energy is the second derivative. Momentum is the first derivative. And if you multiply by I on both numerator and denominator, then it doesn't change the value. But when you multiply I squared, that gives you -1. Okay, and this will go back to the first form. So these two forms are equivalent. You can choose any of them. Kinetic energy operator is a second derivative. In calculus, first derivative is about the slope, and the second derivative is about the curvature. And therefore, if we have a function with high curvature, that indicates a high kinetic energy. A low curvature function indicates a low kinetic energy. Now, a function may have high curvature at some location but low curvature at other places. The observed kinetic energy of a particle is then an average of the contribution from the entire space. The sharp curvature curved regions contribute a high kinetic energy to the average, and the less curved regions contribute only a small kinetic energy. Schrödinger equation is an eigenvalue problem in mathematics. In this equation, we have total energy operator operates on the wave function, give you the wave function back times a constant called eigenvalue. So this is the eigenvalue, and this is the eigenfunction of the operator. So when we solve Schrödinger equation, okay, we use total energy operator, we get eigenvalue, and this eigenvalue is the total energy. Okay, it's the observable. What if we want to find the momentum? If we want momentum, then you use momentum operator. Okay, operates on the wave function. If we get the function back, then this eigenvalue will be the observable momentum corresponding to this operator. Okay, if we want to find the kinetic energy, we choose the kinetic energy operator and operates on the wave function. And if we get the function back, then the eigenvalue will be the kinetic energy. Example: what is the linear momentum of a free particle described by the following two wave functions? One is e to the ikx, one is e to the negative ikx. To find the linear momentum, we use momentum operator, operates on the wave function. All right, and remember you have two forms of momentum operator. We choose one. Okay, so this is the first form, h bar divided by I, first derivative of psi. Okay, and plug in the psi for the a, which is e to the ikx. Now we know the derivative of ex is just ex, and the derivative of eikx will be the eikx. But then your derivative of ikx will be ik. Okay, so that gives you ik times e to the ikx divided by I, so cancel this I, and we have h bar times k, okay, these are constant, times eikx. Eikx is psi, so with derivative of momentum operator operates on the psi, we get the function back. Okay, and therefore this is the eigenvalue, okay, of this operator, momentum operator, and that is the momentum of the system. Okay, so that's the measurement of momentum then will give you the momentum h bar times k. Okay, so in other words, the theory predicts the momentum has to be h bar times k. Now for the second particle, so again we use the momentum operator, operates on wave function, but in this case the wave function is e to the negative ikx. All right, so we derivative it and we get negative h bar times k. Okay, again that's a constant, and we get the function back again, and therefore this is the eigenvalue, and that will be the momentum. Okay, because this is the operator, momentum operator, so eigenvalue is the corresponding observable, and that's the momentum. And therefore you have different sign. For A, it means the particle is traveling in the position x direction, and the other is in the opposite direction because it's negative. In quantum mechanics, all operators that correspond to observables are Hermitian operators. A Hermitian operator meets this type of mathematical equation. This equation just to ensures eigenvalues are real, because eigenvalues are the values of the observables you are going to measure in the lab, so they must be real. Okay. Now we are not going to do lots of calculations, and so you don't need to spend too much time on this equation. But in the future, if we see this equation, I will point out that this is due to the Hermitian operator. The other important feature is that two different wave functions of a same operator are orthogonal. The mathematical equation is the product of one wave function conjugate times the other wave function integration is 0. Now in mathematics, you may learn that when two vectors, okay, is perpendicular, okay, for example, this is 1 and this is 2 vectors, then the dot product is 0. So here two functions product integration is 0, and then we call it's orthogonal. All right, and if it's not, if the wave function both are real function, then you just write I times j, integration is 0. For example, in a hydrogen atom, you have one s orbital, that's a wave function, and you have a 2s orbital, that's a different wave function of the same total energy operator. So these two functions are orthogonal. Okay, they will meet this equation. The wave function product integration is 0. Let's now calculate the momentum of cosine kx. So we use momentum operator operates on this wave function, and the first derivative for cosine becomes negative sine. So sine is not cosine, so when we use momentum operator operates on this wave function, we don't get the function back. Okay, and therefore this wave function cosine kx is not an eigenfunction of the momentum operator. That means this function does not have a definite momentum. If you measure many times, every time you get a different momentum value. Now it turns out that this function cosine kx is actually a sum of two wave functions. We can use Euler's equation to prove it. Let's just skip the steps. All right. The conclusion is cosine kx is the sum of e to the positive ikx plus e to the negative ikx. We already showed that both of these functions are eigenfunctions of momentum. One tells us the wave function has a momentum positive k, h bar k. Okay, so it goes towards the x direction, and the other one is in the opposite direction, negative ikx. And if a function is the sum of the two functions, and we can say this function is a superposition of the two individual wave functions. And even though we know the momentum of the two individual wave functions, but when you add these two functions together, then this wave function does not have a definite momentum. Okay, so if we measure it, okay, sometimes we get momentum h bar times k. Other times we may get negative h bar times k. So if we measure many times, then we get equal amount positive and negative. So the average will be 0. Okay, so we know the average. We can calculate the average, but we don't know each time what momentum we can get. Now, in general, how do we measure the average value, okay, of a wave function? Here is the equation to calculate the average value of an observable. If we want to calculate the average kinetic energy, then in this equation, the operator will be the kinetic energy operator. If we want to calculate momentum, average momentum, this will be the momentum operator. Okay, so we use wave function conjugate times operator operates the wave function, divided by integration, and then divided by the wave function conjugate times wave function integration. Now, if the wave function is real, then this equation just the wave function squared integration in the whole range. According to normalization condition, this should be 1. And therefore, if the wave function is already normalized wave function, then this will be 1. And so the average value for a observable is just the wave function conjugate times the operator, corresponding operator, operates on wave function integration in the whole range. Example, calculate the average value of the position of an electron in a lowest energy state of a 1D box of length L with the normalized wave function given. All right, so you have a box with length L. okay, 0 to L. And the wave function inside the box is described by this equation. And the wave function outside is 0, okay, outside. It asks you to calculate average position. So in other words, if you measure many times, where is the average position of this electron? So we just learned that to calculate average, we use equation wave function conjugate times operator operates on the wave function integration. So here is the position. So here is the position average, and therefore this will be the position operator. And the position operator, if you remember in the table, it shows it's just x times. So here is the wave function, and this is the wave x times this wave function. And because this is a real function, so the conjugate is just the wave function itself. So now you have wave function squared, all right, times x. And if you are interested, you can calculate the integration. And the answer is the integration is L squared divided by 4. And then times 2 divided by L give you L divided by 2, half L. Now the wave function itself here is not eigenfunction of position operator. So if you use a position operator, operates on this wave function. All right. So in this case, it's just x times the wave function, which is square root 2 over L sine pi times x divided by L. And if you do that, it doesn't give you the function, so function back times a constant x c. So it's a constant times c. This is not the wave function times a constant. So because you don't get the function back, so this function, okay, given is not eigenfunction of position operator. In other words, if you measure the position each time you get a different position, it's unpredictable. Okay. However, if you measure many times, the average, the mean value is half L, which is in the center, at the center of the box. What is the expectation value of a wave function that is the sum of two wave functions? Both have defined eigenvalues. For example, the first one has eigenvalue omega 1. Second one has eigenvalue omega 2. All right, so what is the expectation value? Expectation value is also called the average value. So the average value is calculated by wave function conjugate operator operates on the wave function. In this case, the wave function is the sum of the two wave functions. And both conjugate, so you have two functions conjugate added together. And here, C1, C2 are both constant. So we can move constant in front of the operator. So now you have C1 operator operates on psi1. And this, okay, is just because wave function psi1 has defined the eigenvalue. So omega is operator. So operates on the wave function give you the eigenvalue times psi1. Okay, eigenvalue times psi1. Similarly, the operator operates on psi2. It gives you the eigenvalue 2 times psi2. So here you have this equation: C1 eigenvalue 1 psi1, C2 eigenvalue 2 psi2. Now let's distribute this equation. So C1 psi1 times a conjugate times C1. So this term times this term, all right, and that gives you the first one, C1 conjugate times C1 times omega 1. These are all constant. Then integration over psi1 conjugate times psi1. Okay. Now, if it's a real wave function, then this is just the psi squared integration in the whole range. Again, this is the normalization condition, and that should be 1. So the first term here, the integration is 1. Now, what about the second integration? So this is different wave function product. Okay, these two wave function are the wave function of the same operator, and they are orthogonal. So orthogonal means the integration is 0. So the second term goes to 0. Similarly, the third one, different wave function product is orthogonal. It's 0. So that goes to 0. And the last one is the same wave function squared integration. Again, that's normalization condition. That's 1. Okay, so what we get is this equation. The expectation value of the wave function, total wave function, is the C1 squared times omega 1. Omega 1 is the eigenvalue of psi 1, and C2 squared times omega 2. So the interesting thing is the average value is not simply the sum of two eigenvalues. It's psi 1, omega 1 plus omega 2, and that's not the case. Instead, it's the weighted average, okay, sum. So it's the C1 squared. So C1 is the coefficient in this equation. This C1 squared tells you how much contribution from psi 1. Okay, omega 1 belongs to psi 1. All right, so the sum of the two eigenfunctions weighed by the probability that each one will be found in a series of measurements is the weighed mean of a series of observations. You should remember that this wave function is an eigenfunction of momentum, and the eigenvalue is h bar times k. That means that we know the momentum precisely, which is h bar times k. But where is the particle? Okay, what's the location of this particle? To find the location, we calculate the probability at a particular position. So the probability is calculated by wave function squared. So this is a complex number. So we use conjugate times wave function. The conjugate is e to the negative ikx. So the power added together give you 0. E to the 0 power is 1. And the probability is irrelevant to x. In other words, at everywhere, they have the same probability. If probability is the same in everywhere, that means we don't know where is the particle. So here is an interesting situation that we know the momentum, but we don't know the position. Here shows a wave function of a particle with well-defined location. Because if you square this function, you get a high probability at x, but 0 probability at the other positions. Now, in mathematics, this wave function can be obtained by adding several other wave functions. The more you add, the more closer to this wave function with defined location. Or you can say this wave function can be obtained by superposition of infinite number of waves. Now you may remember that if a wave function is a superposition of several individual wave functions with defined momentum, then the total wave function does not have a defined momentum. So this tells us that if the location of a particle is known precisely as this one, then the momentum is completely unpredictable. So the last slide and this slide tells us that at microscopic level, momentum and the location are two observables that cannot be measured simultaneously with arbitrary precision. The last two examples are just cases of Heisenberg uncertainty principle. And this principle says that it is impossible to specify simultaneously with arbitrary precision both momentum and the position of a particle. The mathematical equation is delta p times delta x is greater than h bar divided by 2. Delta means change or difference. So delta p is the uncertainty of linear momentum, and delta x is uncertainty in position. If these two product is greater than a number, then if one is a small number, the other must be a large number. For example, if delta p is small, That means you have small uncertainty of momentum, or you know momentum precisely. Then delta x is a greater number, so you have a large uncertainty of position, or you don't know the position. Here is an example. Suppose the speed of projectile of mass 1 gram is known to be within 1 micrometer per second. Okay, so that's the uncertainty of speed. Okay, speed uncertainty is 1 micrometer per second. The question is, what is the minimum uncertainty in position, delta x? What's the uncertainty, delta x? According to Heisenberg uncertainty principle, the delta x times delta p should be greater than delta h bar divided by 2. And therefore, delta x should be h bar divided by 2 times delta p. And delta p is the momentum, which is mass times speed uncertainty. Okay, so plug in everything, and the speed uncertainty is micrometer per second, should be 10 to the minus 6 meter per second, and that gives you 5 times 10 to the negative 26 meter, and that's a very small number. So position uncertainty is small. However, for electrons, it will become important. Heisenberg uncertainty principle applies to any pair of complementary observables. Suppose we have two operators, omega 1, omega 2. In one case, we use omega 2 operates on wave function. After that, we apply omega 1, so operator 1. And in second case, we use operator 1, omega 1 to operate on wave function. And after that, we use operator omega 2 to operate on that. If in two cases they give you the same result, then the operators 1 and 2 commute. Now, if the two cases do not give you the same results, then the two operators do not commute. A postulate in quantum mechanics says that if two operators commute, then the corresponding physical quantity can be evaluated or measured exactly simultaneously with no limit or on the uncertainty. So apparently the momentum and position, the two operators do not commute, and therefore their observables cannot be measured simultaneously with precision. One way to evaluate whether two operators commute is to define this commutator, and a commutator is defined as this equation. So left side is you apply operator 2 and then operator 1, and second term is you apply operator 1 and then operator 2. So if you use this commutator to operate on a wave function, and if this is 0, then the two operators commute. If it's non-zero, then they do not commute. So if this gives you a non-zero number, then that's not commute. So let's confirm the position operator, momentum operators do not commute. Okay, so we calculate two cases. One is apply momentum operator first, and then position operator. The other one is apply position operator first, and then momentum. So the left side give you first order derivative. Okay, that's the momentum operator, and then times x. In the second case, we apply position operator is just x times wave function first, and then derivative both. And you will see that the second case is not equal to the first case, and therefore you see the two operators do not commute. Okay, we can calculate the commutator, all right, and both apply to the wave function. Again, that can give you non-zero I times h bar times psi. Okay, and therefore the commutator is I times h bar, which is a non-zero. In this section, we introduce the Schrödinger equation, which is an eigenvalue problem. So we use Hamiltonian operator, or the total energy operator operates on wave function, and the wave function come back and times a constant called eigenvalue, and this eigenvalue is the total energy. So in general, if a wave function is a eigenfunction of an operator, then the eigenvalue is the value that you will be observed in the laboratory that is corresponding to this operator. Now the total energy operator includes a kinetic energy operator plus potential energy operator. Kinetic energy operator is a second derivative of the wave function. Potential energy operator is the wave function, or the potential energy multiply. We also learned the meaning of wave function. So wave function does not have a physical meaning itself, but the squared tells you the probability of finding the particle at the position. In a range, you need to integrate to calculate the probability. We also learned Hermitian operator, which means this mathematical equation, and you don't need to spend too much time on this equation. And for a same operator, different wave function, product integration is 0, called orthogonal. Okay, and we learned the expectation value, or the mean value of series observation, is calculated by this equation. Okay, we learned Heisenberg uncertainty principle, which is just a special case for operators that do not commute. And we also learned what is normalization condition and what type of functions can be used as wave functions.